So just as a quick review, completing this square has this general form that x plus some number squared is equivalent to x squared plus bx plus c, where c, right, where c is equal to 1/2 b squared. So for a practical example, what this means is if we have some function, so if I wanted to complete a square for this problem in order to get some form that looks like this, I couldn't do it with this 13 right here. Right? I have to have a form where the c, right, our 6 is b, our c is 13, where the c is 1/2 b squared. And 1/2 of b, which is 6, 1/2 b squared is going to be 9. So in order to get the square for this number, right, I have to add 9 and subtract 9 from our equation. And remember, this adding and subtracting 9 does nothing to change the value of the equation since we're essentially adding 0 here. And so now I can complete the square with this left-hand side of the equation, the x squared plus 6x plus 9, giving me x plus 3 squared. And if you want to verify for yourself that x plus 3 squared is x squared plus 6 squared plus 9, go ahead. And I'll be left with minus 9 plus 13. And 13 minus 9 is just going to be 4, so we're going to get x plus 3 squared plus 4. And that's completing the square for an example like this. But let's do a couple of examples in terms of integration. So when I look at this problem, I see that we don't have anything in the numerator and there's no convenient u substitution. So the best practice is probably to complete the square in the denominator and see if we can simplify this function anymore. And so if I look at x squared minus 2x plus 10, and I'm going to write down here the completing the square formula. So in order to complete the square here, we need to create a more convenient c. And c is defined as b divided by 2 squared. Our b is negative 2, so that makes our c positive 1. And so we should be able to rewrite this integral as 1 over x squared minus 2x plus 1. And in order to keep the value the same, we have to subtract 1. So the value of this integral didn't change at all whatsoever because we've added 1 and subtracted 1, virtually adding 0 to our integral. And now we can complete the square here. So this can be rewritten as 1 over, right? Now we have x squared minus 2x plus 1. This can be rewritten as x minus, right? We have b half, so b is negative 2. We're going to get negative 1 right here. So x minus 1, because we just added a negative 1, squared. And then we have to consider this minus 1 and plus 10, right? So we say 10 minus 1 is just 9, and we add that 9 right there. And now we've completed the square for the denominator. Now, if you're like me, you will notice there is a convenient tangent form right here if I do u substitution. We're going to do u substitution here. I'm going to use a different color just to help remind you. And we're going to say u x minus 1, and I'm choosing this particular u because I know that the derivative of negative 1 is 0, and I know the derivative of x is 1. So we're just going to get 1 times dx, right? And now we can rewrite this integral, right? This 1 and that dx give you a du. So we're going to get a du over, and we now have our u right here, right? We have our u, so we get u squared plus 9. Now we can use our trigonometric integral identities, which says that the integral of this form right here is just going to be arctangent. Remember, and just to remind ourselves, right, the derivative of arctangent x over a divided by a, right, that derivative is this form. It's 1 over x squared plus a squared. Okay? And we have that form right here. Of course, we're not using x, we're using u, and our a is going to be 3 because 3 squared is 9. So this whole integral, right, can be rewritten as arctangent u over 3, right, all divided by 3. And that is our final integral in terms of u. So now when we sub back our x in, we're going to get arctangent of x minus 1 over 3 divided by 3. And now we see that our integral is completely solved. So the next integral that we're going to solve is x over x to the fourth plus 2x squared plus 1. Now, there's no convenient u substitution in this current state, right? We can't sub in x to the fourth plus anything, because then we're going to get 3x cubed, or 4x cubed, and we don't have any form like that seen in the numerator, so u substitution wouldn't work here. We can't exactly conveniently split this fraction, and so our best bet is to attempt to complete the square, right? But if we look at the current form of the denominator when we want to complete the square, we have this x to the fourth plus 2x plus 1, which doesn't look very convenient for completing the square, because the original form that we had was ax squared plus bx plus c, right? That's what we remember learning completing the square in. What you can do is rewrite this integral in terms of some substitution of z, and I'm saying substitution of z because this is not u substitution, right? We're not focusing necessarily on the integral right now. We're focusing just on this polynomial and trying to simplify it. Substituting in something like z. Let's go z equals x squared, right? And therefore we can rewrite this entire polynomial as z squared plus 2z plus 1, right? You see how this is? This is not u substitution. We're not focusing on the integral right now. We're just trying to simplify this polynomial to make it a little bit more convenient. And right here what we have is a squarable polynomial. So we see that our b is 2, and b divided by 2 is 1. 1 squared is just 1. And so we can write a z plus 1 squared in here, right? And you can verify that this squared is this right here. And then we can sub back in our z, giving us x squared plus 1 squared. And you can also verify that if you square this, you're going to get this value right up here. So our final of this function right here is just going to be x squared plus 1 squared. Now this means we can rewrite our integral as x over x squared plus 1 squared dx. Right as I look at this, the first thing that pops into my head is a u substitution, and I'm going to do this in a different color so you kind of remember. Is a u substitution of u is equal to x squared plus 1, right? And my du is going to be equal to 2x dx, right? Because x squared, the derivative of x squared is just 2x, the derivative of 1 is 0, and so our du is going to be 2x dx, which means we have to multiply by 1 in order to prepare our integral for u substitution. So I'm going to do this, right? We're going to go 2 divided by 2, right, times the integral of x over x squared plus 1, right, x plus 1 squared, sorry, dx. Okay, now this x and this 2 and this dx, they give us a du, right? And this x squared plus 1 gives us a u, so we're going to get u squared. You see how that is? And now we have a leftover 1/2 that we have to take care of. And we can find this integral very simply, right? It's just going to be, that's the integral, because u squared in the denominator is equal to u to the negative 2. And when we increase by the power of 1 and bring down that negative 1, we get a negative u to the negative 1. And there's our half right there on the bottom. This can just be rewritten as negative 1 over 2u. And that's our final integral in terms of u. Now we're going to sub back in the x squared plus 1, which is equal to u, and rewrite this. So our final integral, right, the integral of x over x to the fourth plus 2x squared plus 1, our final integral is going to be equal to negative 1 over 2 times x squared plus 1, right? You see how we did that? We basically took this bottom part. We used z substitution, which is different from u substitution, has nothing to do with an integral, but we use z substitution to simplify the expression, substituted back in our x squared, right? That way we were able to simplify the denominator, and we were able to pull out a very convenient u substitution, which we see right here, and simplify our integral in terms of u, giving us a 1/2 because we needed that 2 right there. And then we were able to find the integral in terms of u, sub back in our u as x squared plus 1, and this is our final integral right here.